So propagation is along which direction?
Propagation direction is in this optical fiber, of course, propagation is through the core. Okay. And then along with the cross section, there are two field will be there, magnetic field and electric field. Now, if the electric field is perpendicular, then it's transverse electric and transverse magnetic field. Of course, E and H field also they are perpendicular to each other, and that's why if we take the cross product, there will be a net component. There can be, of course, other components of E field and H field in optical fiber, because though we are taking this is the propagation direction, actually it is propagating little bit zigzagging fashion. So here it will be little complicated the analysis. So at this what will happen, that the total internal reflection condition is not satisfied. Okay. So therefore there will be leaky modes. Leaky mode means the mode will come out of the guiding mode. Okay. So here in this core, in guided condition, if it is straight guided condition, the energy is content inside the core. But if we bend it, some portion of the energy will come out. And if we keep a sufficient length of this cut portion, then that energy will be coupled to this thin metal film depending on the length of the metal film. So it will be coupled to this metal film and come back. Okay, so this going to the metal film and come back is a multiple of wavelength of the light. That portion we have not discussed. So we have to again assume how this coupling occurs, and energy is coupled from this to second waveguide and from second waveguide to the first waveguide. There can be complete energy transfer, and then it will come back, or there can be partial also energy transfer. Both can happen depending on certain conditions of the refractive index of this. Now this metal film refractive index of course has to be appropriately chosen corresponding to the refractive index of the core, such that there is good amount of coupling. Now typically there are more into this technology, because when I bend, the change in the refractive index will change, and then the change in refractive index for these two modes, transverse electric mode and transverse magnetic mode, are different. Two refractive index are not same. So that means effectively the uh, the refractive index is a uh, matrix. Okay, so therefore with that component will can have two dominant component corresponding to these two dominant modes, transverse electric and transverse magnetic modes. Now this thin metal film refractive index is chosen such a manner that it mostly couples the transverse magnetic field mode. Okay. The coupling depends on the refractive index difference of the two guided medium. So that has to be chosen appropriately. Now, once the transverse magnetic field is coupled, then there is a second medium which is also have refractive index matching to the thin metal film. So therefore, it will couple the energy to this high loss oxide layer. So therefore, there will be a loss component will be high for the transverse magnetic component, which has been preferentially coupled to this side. So there will be some amount of transverse electric component will also be coupled, but transverse magnetic field coupling will be more, and loss will correspondingly will also be more. So therefore here when the light is coming out here, the dominant component would be transverse electric component. So therefore we will have a kind of alignment of the electric field in a preferential direction. So So that's why we can say that the output light is polarized. Like if the propagation direction is perpendicular to this and we have Ex and Ey, we call both the components are there. Now if I say propagation is in this direction and I have the polarization electric field only in this direction, then the polarization is light is polarized along this plane. Okay, so that could be some theta angle. Like that, it can be any angle. So this is called linearly polarized light. If both the components are there, we call it the circular polarized light. Because ultimately the E field relates the energy of the light. Okay, E into E conjugate will give the energy. So therefore, in that case, if there are two orthogonal component, the net component E field will be magnitude will be square root of Ex square plus Ey square. So both Ex and Ey will contribute. But if there is only Ex, then that will be only vertical polarized, and if there is only Ey, that is horizontally polarized. Now, if it is polarized at an angle theta, essentially it has equal component of Ex and Ey. So that is polarization. Now, if I pass this light through another polarizer, which has aligned to such that it pass only the orthogonal polarized light, then the net light that will come out of the polarizer will be zero. So that means if I have light polarized in 45 degree and then if I have another polarizer which is having say aligned like this, so then the light coming out here, that should be ideally zero. That if you can two polarizers and rotate, you will find that there will be a maxima point and a minima point, if not complete zero. So that one can see with any two polarizers in hand and rotating against the light. Now that this principle is used here. So here basically what is happening is that the magnetic field, it gives rise to a rotation of polarization of angle by this. This V is the Vedet constant and H is the magnetic field, and the component along the light propagation direction is taken H dot dl by the dot product, and that gives rise to the rotation of the polarization angle. Now, if I want to measure it continuously, so I cannot take another polarizer and rotate by hand or do some mechanical means. So I need to convert it to corresponding intensity, which can be measured continuously. To do that, actually we have a polarizer here. Oh, I think the polarizer is missing. This is the polarizer. So this is a polarizer. So the two component that will be interfere and then that has been passed through a polarizer. So basically polarized light is split equally into two components. by a non-polarizing coupler. Now this linearly polarized light is made circularly polarized using quarter wave plate. Or lambda by 4 plate. So if it is aligned at 45 degree, so then it will give, it will make a linearly polarized light into a circularly polarized light. Both components of circularly polarized light will have a non-reciprocal phase shift, will have a phase shift phi. Phase shift of phi and minus phi. Due to reciprocal Faraday magneto-optic effect. So incidentally, this is also this was also discovered by Faraday. Giving rise a total shift of twice phi. When combined together, at the return, this will produce an interference output of I0 into 1 plus cosine 2 phi. Now again, because of the cosine term, sign information is lost. So whether current is plus I or minus I, so that cannot be determined by this. So therefore the and a phase modulator is used to retrieve this. Say if phi is modulated at omega m as phi m cosine of omega m t, then I modulation would be I0 1 plus cosine 2 phi plus phi m cosine omega m t plus tau by 2 minus phi m cosine omega m t minus tau by 2, where tau is the round trip time. Why it is so? Because you can see that phase modulator is here, okay, in front of this path. So now what will happen, that this component will get the phase modulation tau times ahead of this component, the other component. Okay. So now if we take the reference at tau by 2, so one will have plus tau by 2 and another will have minus tau by 2, because they are separated. Phase modulation is separated by a time tau. So though twice phi, because one is phi, another is minus phi, this is due to Faraday effect. Now this one is due to the phase modulator. But the phase modulator is, one is phi m and another is minus phi m, depending on the direction of the propagation, unlike the Faraday effect. Because, so therefore, so this is plus phi m cosine omega m t plus tau by 2, and this is minus phi m cosine omega m t minus tau by 2. Now this one can be analyzed because it's a cosine of cosine term. So this can be expanded using Bessel's function. This is the modulation depth J0 eta phi m cosine 2 phi sorry. Then the harmonic term will be there, J1 eta phi m sine of omega t into sine 2 phi. Like that, many other terms will be there. So this eta is to sine omega m tau by 2. Tau is that round trip time. So this is equal to n is the refractive index, L is the length of the fiber coil, NL by C. Now lock-in amplifier. Now lock-in amplifier is locked to this component. Sorry, this is sine omega mt. Locked into omega m, locked to into the driver frequency. Omega m. So therefore I lock will be I0 J1m, that is equal to J1 as a function of that Bessel's function of first kind with eta phi m. Sine of 2 phi. Now at eta phi m equal to 1.8, J1 is maximum. Maximum as value is around 0.58. As this eta equal to 2 sine omega m tau by 2. So this can be achieved by fixing appropriate length of the fiber of the coil. Corresponding to a fiber length we have a fixed tau. If that is not in our hand, then we have to vary that modulation frequency. Then FM can be selected. As FM equal to half tau. So these values we can put here, and accordingly we will get that eta value to produce maximum phase deviation. Because that will be equal to pi by 2. So this will be equal to pi by 2. Omega m tau by 2. So this is the basic principle, though while installation of such kind of sensors in high voltage environment, there are insulation requirement. Even if we have optical fiber, insulation requirement is less. Usually it is uh, done with moderate level of insulation. Then other thing is that the optical fiber of the sensing coil has to be also of some special kind of optical fiber which are known as that last day I was talking that for fiber gyro also we use that. Those are called circularly spun optical fiber. So because here we are sensing rotation, so therefore the bending effect while making the coil, that should not affect the overall circular rotation. So to make the overall rotation high, so generally these kind of sensing coils are already twisted and the circular twist is frozen into the fiber, such that we have a large rotation already into the fiber frozen, and then the effect of bending is no longer produce a high uh, a high deviating effect from the circular rotation. So essentially that is to make the circular rotation as the dominant factor in the optical fiber. And then the current produces a small amount of circular rotation, which is or the gyro also produces a small amount of circular rotation, so that is additive to that frozen circular rotation. I think more or less we have discussed the principle. More than this, I think we should not discuss. We have many other topics, and we may have time just 2 days for this optical sensor this week only. So in that we will try to cover two more type of sensor. So one is like you must have heard about OTDR, optical time domain deflectometry, which is used nowadays frequently to know that where is the break point, if there is any break in the optical fiber link. So that principle, that is a common principle, and usually uh, in modern costly buildings, optical fibers are also used for distributed temperature sensor. So yesterday there was a very bad fire in that rail bhavan in Kolkata, and the 10 Gbps fiber link was also down. But if had it been a distributed alarm system, so then that could be probably avoided early. distributed temperature sensor. So distributed temperature sensor is basically can be implemented by laying the optical fiber optical fibers characteristics are fibers are temperature sensitive. In terms of refractive index and absorption. Mainly refractive index gives rise a huge change. However, generally such a huge change, phase change is not useful because it's too sensitive. So it can sense very small temperature change of the order of 10 to the power minus 5 degree, 10 to the power minus 6 degree Celsius. Small change will be sufficient to change in the phase in the optical fiber. So to give a measurable output. However, typically we do not require such a high sensitive temperature change, but generally absorption is used. But then absorption is not that sensitive. So special fibers with erbium doped or neodymium doped fibers are used to make absorption more sensitive. Sensitive to temperature. Now,
Sir, ER is what?
erbium,
Achha, yes.
erbium, and this is neodymium. So typically this doping is done during fabrication. These are called rare earth doped fiber. Also, these doped fibers have other applications like fiber amplifier for long distance fiber communication. But here we are using it as a temperature sensor. So there are two aspects in distributed temperature sensor. That is, one is measuring change in absorption, and then locating the change. So then only it will become distributed. So not only that we measure the absorption, but we also have to locate where it is. So this location is done through time domain reflectometry by radar principle time domain reflectometry. or frequency domain reflectometry. So we shall discuss both of them. Maybe next day we shall discuss about this OTDR and OFDR. And also we need to solve some